So I'm going to be talking about a stochastic process model of deposition, diffusion, and nucleation. So I will explain a little bit about what the model is. First of all, let me say a little bit about where the motivation comes from. And it comes from ultra thin materials. So we're talking sort of nanostructures. So it's quite recent developments because driven by advances in technology and measurement. So things like high-powered electron microscopes, and then trying to use nanomaterials in various applications. So these very thin materials. So think of building films made up of layers of just a few, say, atoms. They have some very interesting properties, sort of electrical or optical or magnetic. And so there's lots of interest in constructing these things. And one way that they can be constructed is via sort of deposition processes. So you start with a substrate and you slowly build up your layer by depositing particles somehow. And so what this talk is going to be about is understanding a very simple model for sort of the dynamics that occur in the early stages as one of these processes. So you have particles being deposited. Under appropriate conditions, they don't stick as soon as they're deposited. They can still diffuse on the substrate until enough of them come together. And at that point, they stick, and that's called nucleation. And so the sort of pictures, so this is these are a couple of microscope pictures. You see the scales here, these quite small scales. So this, the one on the left, is showing the sort of islands that grow on the substrates as you go through this deposition process. So I want to talk a bit about some of a simple mathematical model in this context. So there's going to be three basic elements to the dynamics. We can start with a substrate. Particles arrive, that's the deposition. Particles on the substrate can move around, that's the diffusion. And then when enough of them come together, they stick, that's the nucleation. So that when they come together and stick and nucleate, we call that an island. And these islands, like you saw in the picture, they will slowly grow as they accumulate more particles, and they sort of act as absorbing barriers for the subsequent particles. This model I'm going to talk about is thinking about the very early stages. We're going to ignore the spatial extent of the islands, so they're just going to be single points. That's kind of reasonable early on in the process, but as time goes on, these islands will continue to grow and accumulate particles. So you can imagine sort of at the later stages of this process, we'll be sort of in a different modeling situation. But I want to just talk about this early stage process. So I'm going to take the simplest possible setting, a one-dimensional model. I'm going to take binary nucleation. So just two particles need to come together to form an island, and these islands are going to be single points. Okay, so let me describe a little bit. So before I describe the model in detail, let me say the background in the literature. There's quite a lot of literature about this, starting, sort of increasing with hand in hand with the development of the technology. But certainly since the 1990s, people have been looking at models for these growth processes. And there's various analysis, Monte Carlo studies, some theoretical work, but I don't think there's anything been previously sort of looked at these models from the point of view of formulating a stochastic process model like this. Okay, so I learned about these processes from Michael Grinfalt and Paul Mulheron. Thanks to them for sort of getting this work started. So here's the model. We're going to take an interval, the unit interval 0 to 1, and I'm going to start with 0 and 1 are going to be these absorbing barriers, the islands. And particles are going to be either active or they're captured in the islands. And the dynamics is like this. So deposition is going to be as a space-time Poisson process. So there's going to be a parameter lambda. That's the only parameter in the model, is this lambda, this intensity of this deposition. So that means I'm going to wait independent exponential lambda times between particle deposition events, and then when a particle comes in, it's uniformly distributed on the interval. So that's how particles arrive in the system. And active particles diffuse, so they perform independent Brownian motions until either a particle hits an existing island when it's absorbed, and so that then it hasn't really had any effect on the evolution of the system, or two active particles come together and then they nucleate and create a new island. And then those particles cease to be active, they just stuck and create a barrier for subsequent particles. So, so here's a picture, it looks something like this. So we start with these islands at 0 and 1. We've got this Poisson deposition rate, lambda. And so at some time, an active particle will arrive after an exponentially distributed time, and it will perform Brownian motion. And it might well be that what it does is hit one of these barriers and just gets absorbed. Okay. Something more interesting might happen is that a particle might come in, hang around for a bit, another particle might come in the meantime, and then those two might meet before either of them is otherwise captured, and that would nucleate to form a new island. So this is the basic process that we want to try and understand. And the question is, how does the partition of this interval evolve? So this is a continuum version of a model that's kind of been looked at quite a lot in the literature by Bartelt and Evans and Blackman and Mulheron. And the main goal is to understand the evolution of this interval partition and what can you say about some of the statistics of this process as it evolves. So the sort of things you might want to know is so for example, what is the position of this first nucleation that occurs here, has some distribution on this interval. Then as this process goes on, I could ask the question, which of these two intervals, the left one or the right one, is going to split next? I see there's some stuff in the chat which I haven't been paying attention to, sorry. Is there an additional parameter controlling the diffusion of the Brownian motion? Right, so you could perhaps say there's maybe a couple of additional parameters I could have put in this model, say the diffusion speed of the Brownian motion, and even say the length of the interval. But it turns out that you can scale away both of those effectively into the lambda. I will say a little bit about that later. So really, one parameter is pretty much enough here, thanks. Yeah. So I was saying to describe this interval, how the process evolves. So the one question I might want to ask next is which of these two intervals I see here is the next one that's going to receive a nucleation. So that's the sort of question I'm going to answer. And I want to try and explain how I can describe this interval splitting process in a Markovian way. And that's kind of not obvious that the process I'm going to get here is a Markov process. I'll explain what I mean in a moment. So let me describe in a little bit more detail the results. So I'm going to look at this interval splitting process induced by these nucleations. So nu n is going to be the time of the nth nucleation. Curly z is going to be the vector of island locations left to right. Now this z process, which I'm interested in, is not Markov because there may still be plenty of active particles in the system, which Zn itself is not telling you, and they will be important for the subsequent behavior. But the story is going to be that it's asymptotically Markov in the way that I will describe. So I'm going to describe two sorts of results in two sort of different regimes. The first one is what I'm going to call sparse deposition, is when this parameter lambda goes to 0. So when particles are arriving very infrequently. And then we're going to show that this process converges to a Markovian interval splitting process, and I'll describe what sort of process that is and how it's characterized. The idea is, well, so why is it asymptotically Markov? If lambda is very small, then most of the time there aren't very many active particles in the system. Because so if you think about Brownian motion in this interval, if the absorbing barriers distance order 1 away, then your Brownian motion is pretty unlikely to survive for much more than order 1 time. So if lambda is small, particles are coming in very infrequently, but getting absorbed at roughly constant rate. So most of the time there will actually be 0 or 1 active particles in the system. So this non-Markovian thing that I mentioned before doesn't really, it sort of disappears in this limit. Lambda going to 0 sounds like a very sort of special case, but the second set of results sort of say that actually lambda going to 0 is pretty much the whole story, because for fixed lambda, what we're going to show is that for large time, the statistics of the process are still governed by this lambda going to 0 limit. And you can understand this by saying that as time goes on, the intervals get increasingly smaller. And so actually the capture rate of the Brownian particles increases, or if you like, the survival time of your Brownian particle decreases. Typically, the Brownian particle will survive for time of order the length squared of each of these little intervals, and these intervals get smaller and smaller. The particles are getting captured faster and faster. So this has a very similar effect of sending the lambda to 0. And so I will try and explain that as well. So somehow this lambda parameter is not actually going to appear in any of the results, because somehow the dynamics of the process naturally sort of drive this lambda to 0, at least for looking at certain large time statistics. Okay. Any questions about the formulation of the model before I press on and say a little bit more about the results? Was there anything that wasn't clear? Okay. So let me describe. So the object that I'm going to that's going to appear in the results is, that I said, was this Markovian interval splitting process. Let me describe what sort of object that is. So this is, so I'm going to describe a more general class of processes. There's going to be 2 parameters, a splitting exponent and a splitting distribution. The splitting exponent is going to govern which interval splits next, and the splitting distribution is going to decide, say, where it splits. So think of a discrete time Markov process, talking about partitions of the unit interval. And what you do is choose randomly one of the current intervals with interval of length n chosen with probability proportional to this length to the alpha. So the alpha is telling you how you bias the intervals for selection. And then once you've chosen your interval, you split it into 2 by inserting a point at a relative location according to this distribution phi. So this describes quite a broad family of interval splitting processes. So if I've got a configuration of intervals, this interval of length L will be chosen with probability proportional to L to the alpha, and then I decide to split it by this distribution phi. And this process proceeds in a Markovian way. So this sort of model goes back a long way. In this sort of general framework, there's a couple of papers by Brennan and Duret who do a lot of analysis about the asymptotics of the statistics of these sort of interval splitting models. But there were special cases that go back much further. So if phi is uniform, for example, alpha equals 1 is just uniform splitting. Alpha going to infinity, if you sort of split the longest interval, that's known as the Kakutani process. So there's quite a lot of work on these things. But it's one of these sorts of objects that's going to appear in our limit. And for us, there's the two pieces. There's the exponent and there's the distribution. The exponent is 4, and that's going to be relatively easy to understand, and I'll try and explain where that comes from. And the splitting distribution is something that looks a bit complicated. It's got a density, and the density is given by this Fourier Fourier sort of series. And I will sort of try and explain how this arises. But it looks quite complicated. I mean, it's not even obvious that this density is positive, but it is this thing. So this thing I'm going to call psi will arise from a problem that I'll describe. It turns out to be, it's sort of a defective density, and the total mass is the thing I'm going to call mu. That's the thing I have to normalize by to get my splitting distribution phi naught. Okay. So in the talk, I will try and explain where the 4 comes from. I'll try and explain the how this phi naught arises as well. And I will try and explain what the main results are. So the first theorem is that, like I said, this lambda going to 0 regime, and we're going to say that this process, the interval splitting process induced by this nucleation, deposition and nucleation process, converges to this alpha equals 4 and phi equals phi 0, the ones given on the previous slide. So that's the first sort of result. Here's a picture of this phi 0. So it looks, although the formula for it looks a bit menacing, it looks like a perfectly nice distribution. It looks quite like a beta distribution, and there were certain conjectures that this distribution, or at least relatives of this distribution, should be beta distributions. But in this model, that turns out not to be true. It's something that looks quite like a beta distribution. It has similar sorts of scaling behavior at 0, for example, but it's not actually a beta distribution. For the fixed lambda regime, we're thinking now about large time. And like I said before, large time is going to be effectively the same as small lambda, because gaps are small. So particles don't survive so long. So there's lower density of active particles. And so as time goes on, we're effectively driving lambda to 0. And a precise version of this I'll explain in a bit via a sort of scaling relation involving the parameters. So even for fixed lambda, the limit that I just described sort of drives the long time asymptotics of the process. So formally, you could make some sort of coupling statement to this effect, saying for every epsilon, if you wait for long enough, you can successfully couple your process, the fixed lambda process, with our limit process. I'm not going to write down a formal version of that theorem, but that's sort of one thing you can do. But the implications of this are for things like long time statistics of the process, such as the empirical distribution of gap lengths. So think of the lengths of the little gaps induced by this deposition process. Normalize them so that they've got mean 1, and ask them, so pick a uniform random gap, normalize to have mean 1, what's the limit distribution of that? Or equivalently, look at the empirical distribution of the gaps, normalized to have mean 1. And we can describe the limit for that distribution. We don't have an explicit formula for the density, but we can derive its asymptotics at 0 and at infinity. So that's this theorem here that says this normalized gap distribution as n goes to infinity converges to something which has a density whose behavior at 0 we can understand and behavior at infinity can understand. And the key sort of exponents here, there's a 4 in here, which is the same 4 as appears as our alpha. There's a 2 here, which is related to which is related to the behavior of our psi near zero. So there was a remark here that this psi at zero behaves something like this. So if I have time, I will explain how these asymptotics sort of are derived from the interval splitting process, or at least the class of results that gives this sort of thing here. So, okay. Any questions about those two main results? So first one is lambda going to zero. So I said here, convergence in the sense of total variation, finite dimensional distribution, but think of just convergence and distribution, a relatively strong form of convergence and distribution of this process to this Markovian interval splitting process. For fixed lambda, we can't say very much about the process as a whole, but we can say something about its long time statistics. And you see the lambda does not appear in the limit, and that's because it's the lambda tending to zero limit that describes everything. Okay. So I want to start by looking at the lambda going to zero regime and say, so the structure that's sort of helpful to consider is one of regeneration. So think about, when are the active particles in the system? Sometimes there are no active particles, but then at some point a particle will be deposited. So that's going to be the sigma k here, the time at which the active particle count nudges up to 1. So AT is the number of active particles in the system time t. First time a new active particle arrives, it's going to be sigma k. That particle will hang around for a bit, it will diffuse. Another active particle might arrive in the meantime, but at some point the number of active particles will drop down to 0, and that's going to be the eta k subsequent to the sigma k. There may or may not be a nucleation in that time interval. So in this little picture, where time is running upwards, space is on the bottom, there was a nucleation in that two active particles have come in, they've met each other before either of them met another active particle or the boundary zero of the interval. And so there was a nucleation occurring in this cycle here. So these time intervals I'm going to call cycles, and they're regenerative in the sense that at least up until the first nucleation, these cycles are IID, because every time the number of particles, so if there's no nucleation, nothing has changed in the structure of the islands. So when the system empties, we're back in the original stage. And that will be true between any successive nucleations. We have this sort of IID cycle structure. And so that does some of the work for understanding what's going on. So to explain how interval lengths are related to deposition rate, it's useful to generalize the model slightly to an interval of length L. So at this point, I am going to introduce another parameter just to explain what's going on. And think about this probability here, which is that nucleation occurs on the first cycle and at a point in some set B. So I've chosen it so that B is a set living in the unit interval, so LB is in this interval of length L. So this is a probability that will depend on the L, will depend on the lambda, and will depend on the target set B. But this is just looking at the first cycle. So to understand the lambda going to 0 asymptotics, I claim there's two things you need to understand on top of this regeneration structure. And the first is scaling, that tells you how you can change lengths, so sort of move parameters between the length and the deposition rate. And so this appearance of this L cubed will be important for sort of understanding where the 4 comes from. So I will say a little bit about that. And then the other thing you need to understand is how this probability behaves as lambda goes to 0. And I claim it goes like lambda times something, and the something is the splitting distribution. So these two relations here are going to be the origin of the 4 and the origin of the phi naught. So the two parameters that govern the interval splitting process. So, and these are just properties of this single cycle probability. So the thing that ties it all together is the regeneration. So I will try to explain how these two relations give you the 4 and the phi 0. So think of sitting in a configuration where I've got some islands already, and I ask the question, which interval is going to split next? So what's the probability of nucleation occurring in the interval I've indicated in the first cycle? Well, one way it could happen is that the first particle to arrives in that interval, and then nucleation happens in the first cycle. So there's an extra L that comes from that initial particle arriving, and then I multiply by this one cycle probability, and I claim that that's pretty much the most likely way that this nucleation could happen, because anything else involves nucleation occurring in an interval other than that containing the first arrival, which would be a sort of order lambda squared event here, and we're going to be sending lambda to 0. So when I say an error term, I mean error term in terms of lambda. So we get an L from here. By the scaling relation on the previous slide, that gave us an L cubed, and together this gives us the L to the 4. And I've got the phi that I said was the asymptotics of this probability as lambda goes to 0 for the L equals 1 case. So this little argument combining this scaling relation and the asymptotics for this probability over a single cycle is essentially the origin of the parameters in this Markovian interval splitting process, the 4 and this phi 0 distribution. So that was talking about in a single cycle, but the regeneration property sort of implies that if it doesn't happen now, you toss your coin again, and it's sort of this will give you essentially that the next nucleation occurring here is proportional to it doing so in the first cycle. So let me talk about those two things that I said would sort of give you this result. The first one was scaling. Probability nucleation occurs on the first cycle, and the point is to LB. So I claim that this, if you look at an interval of little l of length L, is the same as looking at an interval at rate 1 and just running your Poisson process a bit at a scaled by a factor of L cubed. And to see that, it's just a combination of the scaling properties of the Poisson process and the Brownian motion. So there's a little picture here, which is maybe a little bit too small. But basically, you start with Brownian motion of rate 1 on an L interval. If you scale space to shrink that interval to length 1, then you scale the rate of the Poisson process, you scale the rate of the Brownian motion. And then if I change time to get back to rate 1 Brownian motion, you just follow it through and see what the rate of the Poisson process you end up with at the end is, and it's this L cubed lambda. So and for this reason, you can scale out parameters such as the length of the interval or the rate of the Brownian motion and basically put everything in the lambda. the second component is actually understanding the asymptotics as lambda goes to 0 of this probability. So nucleation occurs in the first cycle and at a point in the set B. So here, there's a calculation to do. So I'm going to claim a certain mechanism that dominates the lambda going to 0 asymptotics. And maybe I've got essentially the same text here, but with a picture. So I claim that the sort of first order asymptotics are given by something like this. So I'm in the interval 0, 1. I want to know what's the probability that nucleation occurs in this cycle. So before, when the first active particle arrives, I want nucleation to happen before the number of active particles drop to 0. And I'm also asking it to happen in a particular set, so a particular location in the interval. And I'm say that the most likely way to do this is that the first particle arrives somewhere, survives up until some time t, when the second particle arrives somewhere, so at some other location z, and then those two particles, the first particle by time t has got to somewhere else, call it y, and then I've got two particles, one at y, one at z, and they've got to collide in B before either of them exits the unit interval. Now, there are other things that could interfere with this, like other particles could arrive in the meantime, so on. But I'm saying that in terms of as lambda going to 0, this is the thing that's driving the probability. So, and we can describe this event now with a little bit of notation. So I'm saying I want first Brownian motion to survive for a bit, and I need to know where it is at the point when the second Brownian motion comes in. That is given in terms of this thing I called Q, which is the density of Brownian motion conditioned to survive, so in a unit interval with absorbing endpoints, conditioned to survive for some time. What's the probability of finding it around y? And then I'm asking for particles started at y and z to meet before either hits 0 and 1. And this is integrated over x, the initial point of the first particle, which is uniform, integrated over z, the initial point of the second particle, which is uniform, integrated over t, which is the point times the exponential density, which is the time at which the second particle arrives after the first arrives. And then what else? 1, 2, that's integrated over that, and also integrated over y, which is the location of the second particle at the time at which the location of the first particle at the time at which the second particle arrives. So there's some analytic expression here, and all of the bits in here we can sort of understand. But the main thing I want to say at this point is that we can understand the lambda goes to 0 asymptotic. So where does the lambda appear in here? It's just the lambda e to the minus lambda t. So as lambda goes to 0, this is lambda times something. And this something I'm going to call phi1 of B, some defective distribution, it turns out, on the unit interval. And I claim all the other mechanisms that could require nucleation are going to demand 2 arrivals after the first, and those will be little o of lambda, because each time I ask for a new particle to arrive, that's a factor of lambda. So what remains is basically to show that this thing I called phi1 and derived from these probabilities involving Brownian motion is the thing I showed you, the phi0. So here I will just say where this comes from, and it comes from thinking about an exit from triangle problem. So this thing with the many integrals was the thing we wanted to compute. The Q, this density, defective density for absorbed Brownian motion, is something that is known. The other thing, the thing saying start 2 particles, what's the probability they meet somewhere before they exit the interval? I think it's nicest to think about this in terms of a 2-dimensional Brownian motion in a triangle. So if I take those two Brownian motions and think of them as coordinates of a planar Brownian motion, then this is the same as saying I start in a right-angled triangle, planar Brownian motion from a point YZ, and I want it to hit the diagonal, so that's saying the two coordinates coincide, before either of the other two sides, and at a particular set B in the diagonal. So this is an exit problem for planar Brownian motion, and this can be solved by method of images for the Dirichlet problem. So these particular boundary conditions, we didn't find the solution written down anywhere. There's a closely related paper by Smith and Watson, 67, where they look at not started from a fixed point, but started from a uniform random point. That's quite close to what we're doing, except we're going to have to integrate over a different density than the uniform, because we have this Q thing instead of in here. So we know everything that's in this thing. It looks quite bad because, well, there's four integrals and the objects that are appearing in them are both infinite series involving some things, but it's actually not so bad. I mean, so it's not so surprising maybe that something complicated comes out, but it's something not too complicated comes out. It's just this psi, which has this relatively compact Fourier series representation here. So this is the origin of this defective density. It's this exit problem from a right-angled triangle integrated against this Q. Okay, so in the last sort of 10, 15 minutes or so, I will say a little bit about how this same process goes on to describe the fixed lambda long time. Okay, so I've sort of tried to explain where the elements of this interval splitting process come from in the lambda goes to 0 case. But for fixed lambda, we don't have the same nice property in that, at least early on, we might have many particles in the system. We don't have this nice description of the mechanism for nucleation. We can't ignore order lambda squared terms. But still, if we're only interested in large times, we get back essentially the same sort of description, because for large times, gaps are small. We can think about it in terms of the scaling relation. For small L, that's the same as driving the lambda to 0, because we said there's this interchange between the length and the deposition rate. So the idea is that for large times, the fixed lambda process should still be well approximated by the lambda goes to 0 process. So to follow through this idea needs some more work. So we need to get some more sort of quantitative estimates in the previous arguments that I sort of sketched out. And we need to analyze statistics of the interval splitting process to get things like good asymptotics for the normalized gap distribution. So I'm not going to say so much about those details. I will maybe just explain that, so in the context of the interval splitting process, we wanted to derive statistics for the lengths of the gaps, the empirical distribution of the gaps of the interval splitting process after a long time. So we did that for this sort of Brennan and Duret fairly general class of interval splitting process. So we could sort of see what characteristics of the interval splitting process were important for the asymptotics. So if you have a general interval splitting process with an exponent alpha, which for us is going to be 4, and a splitting distribution phi, it turns out the only thing you need to know, though the thing about the splitting distribution that governs the gap statistics is its behavior near 0, supposing it's, say, a symmetric density on 0, 1, and suppose that it has a particular behavior at 0, so it goes like something like b times x to the beta. So in the Brennan and Duret work, they have a characterization of this gap distribution via a fixed point equation. And so we just need to do a bit of analysis to extract the asymptotics from that. And the details are not so important, but there's a general result for this class of interval splitting processes that shows how these asymptotics depend on the alpha and depend on features of the splitting distribution near 0. And so for us, this alpha is equal to 4, and this beta was equal to 2. And you see the beta appears in the near 0 asymptotics of the G, the limiting density of the gap distribution, and the alpha appears in the near infinity asymptotics. Okay. So this splitting density that has this Fourier series representation, let me just say a few remarks about this. So this is this density phi 0, this distribution phi 0, which was written in terms of this density psi, which is this defective density that comes out of this exit from a triangle problem for the Brownian motion. So it has this Fourier series representation. So I didn't spend much time sort of discussing this in detail, but it's a sum over odd n of something involving hyperbolic tangent with a 1 over n to the 4 and a n to the 3 in there, and then these sine n pi z's. This is a defective density. It has total mass mu, and so when the thing that appears in our splitting process is a genuine distribution, so you divide by the mu to get back. So the mu is the integral of this psi, which has a relatively compact form in terms of this sesh squared. So there's some quite nice quite nice theory behind these sorts of series. If you tweak the powers of n, sometimes you get nice closed form things, and sometimes you don't. So this sesh squared over n to the 4 is one of them, for which doesn't seem to be a nice relation to a simpler function. Whereas I think if this was a 3, for example, it would have been a nice formula. But this so I don't think there's any particularly nicer formula for these objects other than these infinite series. But you can work out the moments of this distribution, for example. So it's symmetric. So the mean is a half. You can work out the second moment, third moment. They have reasonably nice closed forms, other than they involve the mu, which doesn't have a particularly nice closed form. And then fourth moment, you get another one of these sesh squared series with a power that isn't particularly conducive to simplification. However, this Fourier series form here is not so great for numerical computation because it's decaying relatively slowly, this 1 over n cubed, 1 over n to the 4. So there is a more efficient representation, a much more efficient representation for numerical computation. So again, I won't say much about the details, but you can re-express this psi in a nice way using some classical series expansions for this Clausen function, which is sine nx over n to the k, cos nx over n to k, and its relatives. So you can get a formula that you can get a expression which converges, a series expansion that converges much faster. So that's how we did the numerical plot of this density. Okay, so just to finish off, last 5 minutes or so. So we started with this motivation in terms of this thin film growth model. This model we've looked at is kind of the simplest one you could look at. We've taken one-dimensional interval. We've taken binary nucleation, so just two particles need to come together to nucleate. So really, this picture here, for example, this is a two-dimensional substrate. I mean, kind of the islands sort of do extend into the third dimension, but really we would at least like to understand the two-dimensional model. That's kind of the most physically relevant. And also you would like to extend this to higher nucleation thresholds. So instead of two particles coming together, say maybe three need to come together for nucleation, or four, or whatever. But there's some problems as soon as you try and make these extensions. So formulating it in terms of these Brownian motions, if you're demanding three particles come together, then that's not really going to happen. And certainly, and even when you go to higher dimensions, even two particles coming together is going to be problematic. So it seems like to extend to these more realistic, perhaps, well, at least so to extend to higher dimensions or to increase the nucleation threshold, you might need to introduce some sort of interaction radius or size. And then it gets more complicated, because then it seems like it's natural that your islands actually do have spatial extent, and so space starts to fill up as time goes on. And so you're going to have to be much more careful about trying to identify a regime for asymptotics. Higher dimensions. Okay, so that's pretty much the story I wanted to tell you. So thank you very much for your attention. I'll just finish with a couple of pages of references. So there's the Brennan and Durrett work on splitting intervals. There's the previous work on modeling some of the references on the diffusion out of triangle. It's a nice paper, and some references on the motivation as well. Thank you very much.